So, oh, why are you not? Oh, there it goes. So I need to finish this lecture, and obviously I did most of it in class. So it was dealing with cladistics, which is attempting to organize all of life into a tree that we can use for taxonomic purposes. And what we were attempting to figure out is, well, how did we get to these relationships? And we dealt with all this stuff. And this is where we ended. So basically, that whenever we create one of these cladograms, which are just a document or a diagram that shows, here's how we think all of life is related to itself. If you make it all the way out to the edge, we call it an extant species. If you didn't make it that far, you're an extinct species. To put this thing together, what you need to do is test it out. So how do I know that A is better than B, or that B is better than A? Well, the answer, of course, is parsimony. Parsimony turns out to be the winner. And the way that you could do that, as I pointed out in 5th period, I didn't point out in 0 period. If you were to take each of these species, I'll pick one because I just picked it in 5th, which were the rodents, rodentia. If I were to look and see how many branch points there turn out to be in order to reach the rodents, on A you have 1, 2, 3, 4, 5, 6, 7, 8 branch points that need to show up before we get to rodents. If we look on the right, we have 1, 2, 3, 4, 5, 6, 7 branch points. So for the rodents, B is easier. We have to take fewer turns, which means it is a better answer. It is more parsimonious. But that's just for the rodents. I would need to do that for every single one of these organisms that turn out to be up here in order to actually figure out, is this really the right combination? And that is why we have to use computers. What makes this complicated is, well, where are we getting our information from? Well, when we look at our sources of evidence, sometimes we go off of structural issues, as you would see here, but sometimes we also turn out to use DNA, or we'll use proteins, or we use things that we cannot actually see ourselves, and we're inferring stuff based upon what's left behind. And that, of course, would be a fossil. So the only way that we can look at anything from the past is we have to look at fossils. So we have to say something about a fossil. If you become a fossil, odds are, well, number one, it's very rare to become a fossil. The evidence of that is, even if we look around today at how many organisms there are, the fact that they're not all burying up on the earth, they're all just disappearing on us, meaning they're decomposing, tells us that not everything becomes a fossil. It seems to actually be a very, very, very small fraction of whatever exists becomes a fossil. So what you need to have is something die on a riverbed. So automatically we're going to be really, really harsh towards anything that does not die in riverbeds. The reason why it needs to be a riverbed where the death occurs is in riverbeds it has been well documented that sediments build up. And by building up those sediments, what you can do is slowly cover up the decomposing body. What that will result in is the soft parts will go away and you're left with the hard parts. Those hard parts then need to become exposed so we can find it. If we don't have these combinations of things, it makes it much harder to find a fossil. So if you had a footprint as a fossil, that means you had to have a footprint placed into an area where it could be covered up with sediments, and the footprint needs to be in a different composition than what's around it. It needs to then be covered up, allowed to cement, and then become exposed. The odds of becoming a fossil are incredibly slim, which automatically leads to this issue. And that is, if we perfectly well knew everything that happened, let's assume that this far left, this is exactly what happened. We have 3 extant species, 1 extinct species. The problem becomes, we don't get to see every bit of transitionary species in between to connect all these dots. We don't get to see the microevolution that occurs between these branch points, or the rapid pieces of macroevolution, of speciation. We don't get to see it by virtue of the fact that not everything becomes a fossil. Automatically, we need to start erasing away large chunks of my connecting lines, to the point where all we get to see is this third panel. which is we have some things down here, we have some things up here, we might have some connecting points. And what we then need to figure out is, well, how do you connect all these pieces back together again? And sometimes, as you see here on the right, we can get it right, or we can we can get it wrong because it doesn't happen to match. Or we get more information and we find and realize, oh, these two don't need to be connected to each other. In reality, these two, this one here for 2 needs to connect down to the bottom. So, we need to redo what we think was happening. And that's because we don't have a complete fossil record, and we never will have a complete fossil record. If we keep waiting for a perfect fossil record, it's never going to happen. So what we need to do is work with what we have and do the best we can, because the fossil record, by definition, is imperfect. But that doesn't mean that we can't figure out what's going on. What we have learned, if we look at the fossil record, is if we look at just the types of fossils that we see, meaning patterns on how skulls look, or patterns on how fins look, or patterns on how gills are formed, or whatever, or patterns of soft-bodied structures and what they look like. What we see is if we were to count up all those different things that we see and add them up, what we turn out to have are these big die-offs in terms of numbers if we look at things over the age of the rocks. Because when we say millions of years before present, what we mean is we're looking at rocks, because we assume that if you die in rocks, in a layer of rock, and we look at it sometime from now, and we date those rocks to be 5 million years old, we're assuming that you, who died in that layer, are also 5 million years old. It's a very logical assumption. It's one of those where, could it bite us back? Sure. But you have a lot more things that you need to be able to explain than just saying, hey, if the rocks around the fossil are this age, clearly you're the fossil is the same age as those rocks. What we learn is if you sit there and measure all the things that kind of keep dying off on us, is most of life that has ever existed does not exist anymore. If we look at the way we have die-offs. So die-offs deal with numbers of families. Families then can translate into species. You can have a family that has one organism in it. So saying, this here turns out to have something on the order of 500 families, well, that could possibly be 500 species. If we look at this, we've had 5 major die-outs in Earth history. And they have names, and honestly, who cares if you can remember the Ordovician, Devonian, the Permian, Triassic, and the Cretaceous. Most people don't refer to as the Guadalupian, as in, I've never heard of the Guadalupian. I know of the Permian one. If you were to look at the species over time, what we realize very, very, very quickly is that most things that have ever existed do not exist anymore. All the Cambrian things are gone. Most of the Paleozoic, meaning even beforehand of the Cambrian, are gone. The Paleozoic is also Precambrian. And then even then, when you look at the modern things, a good chunks of them are gone. Most of life is gone. They have undergone mass extinctions. And even when we look at how many things are dead, we still don't have that many fossils. We have lots of fossils, don't get me wrong. But if you're waiting for every single transition species or every single transitionary form to be found, well, good luck. Because there are a lot of things that just do not turn into fossils. Doesn't mean they weren't there, just means we can't find them.